So, this is Chapter 4, Section 1, the development of a new atomic model. So, let's talk about where we left off. The last time we have talked about atomic theory, we had looked at Rutherford's model of the atom. And according to Rutherford, we had a nucleus that it was small, dense, it accounted for the mass of the atom, it contained positively charged particles named protons, and it contained particles also called the neutrons, which have no charge at all. Okay. So, and then outside the nucleus, we have this electron cloud where electrons are found. So right now there are some disadvantages to Rutherford's model. First of all, it doesn't explain how the electrons are arranged in the electron cloud. And if we go back to maybe middle school or even elementary science, we know that oppositely charged particles attract. So this means that those negatively charged electrons should be drawn toward the nucleus, and that doesn't happen. So we don't have an explanation for that either. All right. So this brings us to new evidence. So we are going to talk today how light behaves as both a wave and a particle, and that tells us that electrons have this duality behavior also. They behave as a wave and a particle. So last week you would have looked at how they behave as waves. We know that they have a wavelength and they have a frequency, and that wavelength and frequency are inversely proportional. And so that brings us to our equation for today. We're going to look at the speed of light equation today. So the speed of light is represented by the lowercase letter c. It's a constant value, which means it's always the same. It has a value of 3.0 times 10 to the 8th meters per second. So you'll be responsible for memorizing the value for the speed of light. And if I take and multiply the wavelength, which has the Greek letter lambda, times the frequency, okay, this will be equal to that constant c. So that brings us to our problem here. So I want to know what is the frequency of red light. And the red light that we're looking at it has a wavelength of 6.5 times 10 to the negative 7th meters. So this is my equation that we're going to use. We're going to plug in the value for c. Right. The value that's given to me is the wavelength, so I'm going to plug that in place of lambda. Then we're going to solve for the frequency. So according to my algebraic rearrangement, we want frequency by itself. So we're going to divide both sides by 6.5 times 10 to the negative 7th meters. So we'll be left with frequency on this side. And my meters unit is going to cancel. So the unit I'm left with is 1 over seconds. And that is actually the unit that we use called hertz. All right, so I'm going to take my speed of light and I'm going to divide that by my wavelength. And both of these numbers have two significant figures. So my answer should have two sig figs. I'm going to get 4.6 times 10 to the 14th hertz as my final answer. Okay, so we talked about how light behaves as a wave. Now, all of the behavior of light cannot be explained by the wave theory. So we need to look at another theory for how light behaves. And so this would be the particle aspect of how light behaves. And so what we're going to look at here is the photoelectric effect. Right? So in the photoelectric effect, here's what we have in my drawing. We have a metal, and we know that these negatively charged symbols are electrons. And we have light that's hitting a metal. And if the right frequency of light hits the metal, then this kicks out electrons. Now, there's a few things we need to talk about in terms of the light and the metal. So for this to happen, there has to be, this light has to have a certain frequency, and the frequency is dependent upon the metal itself. Now, we should know from last week's discussion that frequency and energy are directly related. So if I'm talking about having a specific frequency, it means this has to have a specific amount of energy also. And in terms of a metal, it's also determined about how tightly those electrons are bound to the metal. So we'll get to a point in chapter 5 where we'll talk about trends in the periodic table. And one of the trends that we'll discuss is the idea of being able to kick out electrons. All right, so this is how scientists knew that the wave theory didn't explain everything. So if this was really true, that energy was emitted as waves, so this is my squiggly lines in the picture, then my electromagnetic energy would be continuous. But this is not what we saw with the photoelectric effect. So the scientist responsible for this explanation is named Max Planck. And he suggested that energy is emitted in packets called quanta. And he represented this energy with an equation that looks like this. E, which is representing energy, is equal to H. And so H is representing what we call Planck's constant. And so it always has a value of 6.626 times 10 to the negative 34th joules times seconds. So you'll be in charge of knowing Planck's constant. And then The rest of this equation, we're going to take Planck's constant and multiply by the frequency. All right, so let's look at our equation related to that we just looked at. So I tell you that I have a photon of light, and we're going to define the term photon here in just a second. And I tell you it has an energy of 3.2 times 10 to the negative 19th joules. So we're going to plug that in for E in our equation. And we're going to want to know the frequency, and H would be Planck's constant. So we want frequency by itself, so we're going to divide both sides of our equation by Planck's constant. So it cancels here, so we're left with frequency. And then on this side, my joules would cancel. So again, we're left with units of 1 over seconds, which is the hertz. Okay, so we're going to plug in our calculator. And it looks like the energy we were given has the fewest amount of significant figures, which is 2. So we're going to get 4.8 times 10 to the 14th hertz as my final answer. Okay, so after Planck made this realization about the photoelectric effect and the idea of quantum of energy, Albert Einstein comes along and he introduces the idea that light behaves as a wave and a particle, and that each particle carries a quantum of energy, and he called those particles photons. So that photon is a particle of electromagnetic radiation, so it's energy. Energy is not matter, so it has no mass. And that particle has a quantum of energy. So in other words, that particle is containing a specific amount of energy. And so we came up with this idea also that when my matter absorbs energy, it's absorbing a quantum of energy, and the amount of energy it's absorbing, it has to release that same amount of energy. So we're ready to look at our next experiment that made advances in terms of our model of the atom. So here's what we see in the picture. We have a gas discharge tube. So basically my tube is filled with hydrogen gas. And it is connected to a power supply. Now, this is providing energy to our electrons. And we can do that several ways. So we could talk about supplying energy through electric current, which is what we're doing in the picture here. We can even use heat. So when we're going to be in the lab sometime soon, we are going to use a Bunsen burner. Okay, so here's what happens in to the atoms of hydrogen that are in this tube. Okay. We know that hydrogen has one electron. So if I have one hydrogen atom, it has one electron. Okay. And that electron is going to absorb energy. And when it absorbs energy, the electron is going to move to a higher energy level. And the vocab term for this is we call this an excited state. Now, this excited state is unstable, so electrons cannot stay there. So they then move back to their ground state. And their ground state would be the original energy level that electron would be located in. It's also important to note that the higher energy level, those are have several different excited states that are unique to an element, but the ground state just is one. So every element just has one ground state. Now, when it moves to this ground state, the amount of energy that was absorbed is now released. So this was really what Einstein was referring to. The amount of energy being absorbed has to equal the amount of energy that's being released. And the amount of energy released has a specific wavelength and frequency, so we would see a very specific color of light. Now, the best way to explain this to you is think of those neon signs that you see. All right, so this is how we get that pink color. But then we take that light and we shine it through a prism. So that's what we see next in the picture. And that prism breaks apart light into very specific wavelengths. And this is known as a line emission spectrum. And so line emission spectrums, these are unique for every element on the periodic table. So the best analogy I can give for this is you have fingerprints that help identify who you are. Right? The line emission spectrum for an element is like their fingerprints. That's how we identify elements. So this is what astronomers use in order to determine what elements make up specific stars. Now, remember, with all scientists, all experiments, we've talked about what our observations are and what conclusion we were able to draw from this so that we can expand our model of the atom. So here's our observations. That we can see that only specific frequencies of light are emitted. And based upon that, here's what we conclude about our model of the atom. It tells us that electrons exist in specific energy states. So now we know something about the arrangement of the electrons within that electron cloud. So from the emission line spectrum, we have come to our new model of the atom. So this is Bohr's model of the atom. And Bohr was a physicist. And here's kind of the key characteristic of his model. The first thing he claims is that electrons are found in orbits. So in my picture here, those orbits are represented by n. So you can see n is equal to 1, n is equal to 2, all the way through 7. Right? You can see that they are outside of the nucleus of the atom. So the best analogy for these orbits is a ladder. So you know that the rungs on a ladder, you can step on the rungs, but in between the rungs are empty space that you cannot step in between. So this is the same thing being said about electrons. Electrons can be found in specific orbits, but they cannot be in between orbits. The next thing he said was about the orbits themselves. He says that each orbit has a fixed amount of energy. And so the energy relationship here is that orbits that are closer to the nucleus have a lower energy. And orbits that are further from the nucleus have a higher energy. And so he actually calculated this energy relationship, but we can really talk about it using our emission spectrum for hydrogen. So if we look, hydrogen's line emission spectrum, it gave off a wavelength in the violet spectrum. So we know from our discussion of electromagnetic radiation that violet light has a short wavelength and a high frequency, which means it has a high energy. So you would have to have a big energy difference between the excited state and the ground state to get that wavelength of light. Another component that we observed in the line emission spectrum for hydrogen is that it has a red wavelength of light. So we know that red has a short or a long wavelength, which gives it a low frequency. It would be a low energy wave. And so in this case, it would have to have a small difference between the ground state and the excited state. Now, there were some disadvantages to Bohr's model. So this is not our final model of the atom. The big disadvantage at this point is that it only explains the element hydrogen. And this model of the atom does not explain chemical behavior. Okay, so this will be the end of our notes for chapter 4, section 1. Our next set of notes, we're going to look at our current model of the atom, which is the quantum model of the atom.